Good afternoon, everyone. My name is Addnan, and I am a Master SISE student. Today, my internship topic is development and characterization of soil gel waveguides inscribed by UV photolithography. And my supervisor is Dr. Maxime Boyom. First of all, I will outline my presentation. I will talk about introduction, then experiment and characterization and results. And finally, I will conclude my presentation. So the objective of the internship is that to develop and characterize soil gel waveguides inscribed by UV photolithography. These waveguides are used to functionalize surfaces in order to serve as damage detectors for aircraft. Now I would like to talk about Addon. In the framework of Clean Sky 2, the project Addon, which is acronym of Advanced Damage Detection through Optical Sensor Network, we have to create a 2D soil gel waveguide which can be implemented on aircraft such as wings. For example, when this 2D waveguides will be implemented on aircraft, so if there is any defect, for example, here this is a circle, and we can see if there is a defect here, and when we will inject light here, then we will, hello?
Yeah.
Okay. And then we will not be able to see optical modes here and here. So with the help of 2D mapping, we will able to localize our defect. So this is the main aim of this project. So since we know that aircrafts fly in the stratosphere layer of the atmosphere, and in this layer, the temperature is close to -55 to -5 degrees Celsius. So, so the aim is to check if this waveguide can resist such temperature range. So I will be probing temperature range from troposphere to the stratosphere layer of the atmosphere. So for that, I have used an oven. In that oven, I have created a program, and so so first the starting point of temperature is 20 degrees Celsius, and we kept 1 hour temperature difference, 1 hour time between each temperature difference, so that our sample will be stabilized. So first temperature will increase from 20 degree to 60 degree, then it will decrease from 60 to -40, and then it will again increase to 20 degree, hence close to the real life situation. So also after each thermal cycling, we will also observe optical microscope and acquisition of guided mode to check if there is any crack or damages. So now I will talk about the creation of silicon and dioxide titanium dioxide waveguide. So we used a soda lime glass substrate. On that substrate, we used spin coating technique to deposit our solution, and then we did the pre-thermal treatment at 60 degree for 5 minutes to evaporate the solvent or to pre-densify the layers, and then we did UV insulation to polymerize or densify the layer. And then we did development with the butanol to remove the unpolymerized part. And finally, we did the final thermal treatment at 90 degree for 30 minutes to stabilize the final device. So now I will talk about different techniques for UV photolithography. There are two techniques. First one is amplitude mask technique, and second is direct laser writing technique. Here in amplitude mask technique, we made UV exposure using U wave lamp operating at 365 nanometer on an unpolymerized solution. Then we did development with butanol to remove the unpolymerized part, and the remaining part is the final device which we will obtain. And the second technique is direct laser writing technique, which used the last facility in this technique. Here the principle is that we have a UV source which is fixed, which is at fixed position, and it is operating at 375 nanometer wavelength. So the sample will be placed on stages, and these stages can move in X direction or in Y direction, and with the help of movement we will create waveguides, and these black lines shows the polymerized parts, hence this way we will create waveguide. And one more thing, I used here direct laser writing technique because this technique is applicable for large surfaces, while this amplitude mask technique is not applicable for large surfaces. So this is the typical figure of a 2D soil gel waveguide. It is a 40 by 40 centimeters square. And then I did the characterization. So first one is the optical mode. So here I used single mode optical fiber 28, and we placed our sample here, and then we inject light by using super continuum source whose range is from 200 nanometer to 2 micrometer. So we inject light using optical fiber in our sample, and then we will, with the help of microscopic objective, we will capture the optical modes. So this is the image we have obtained before thermal cycling, and after first cycling it is this image, and so on. We have performed this 21 cycles, and you can see that there is no change in optical modes. So modes are intense, and we can also say that there is no effect of thermal cycling. So we can it is a good result. And the second characterization is microscopic images. Here I have used SISE so to check the structure. So this is the structure before thermal cycling, and this is the structure after 21 cycles, and you can see that the structure is very well retained. And we also measure dimensions, and that dimensions are also nearly identical. So, and we can say that, and there is no crack or dilatation here as well. So finally, I will conclude my presentation. So I have successfully created waveguides using photolithography and sol gel technique. I have also checked that optical modes are not affected by several thermal cycling, which means that this waveguide can operate at different temperature range, and it is suitable for aircraft application. Thank you for your kind attention.